Yeah, sure. Hi, everybody. This is Matt. He's my student, and he is going to be talking today about his work that he's done on thermal state preparation and ground state preparation using heat interaction models that have only one qubit requirement, as opposed to many of the other approaches that we've seen that are memory hogs. So take it away, Matt.
All right. Thank you, Nathan. Thank you, Devera. So yeah, like Nathan mentioned, this is going to be a quantum algorithm. So we're going to be focused with how do you simulate quantum systems on digital fault-tolerant quantum devices. But there is connections with this repeated interactions model from the open quantum systems literature. So you can sometimes kind of abstract it to that kind of setting. Okay. So the repeated interactions model, if you've never seen it, is a setup kind of like this, where you have your quantum system where you're trying to thermalize or cool down. And you maybe have a single photon that might interact with your system, and then it scatters and goes off. And then you have another photon that comes on, interacts, and rinses and refreshes. And the idea being that if you repeat this process enough times, eventually the system will thermalize to the same temperature of the photons that it is interacting with. Could be photons, could be a spin, could be some kind of just small quantum system. And so although this is kind of a model study in open quantum systems, the inspiration that we took was more of a classical algorithm. So this is a classical algorithm for sampling from thermal distributions or thermal states or probability distributions more generally. And we took this classical algorithm and tried to port it over to quantum. So I'll mention this inspiration. Then I'll probably spend the most of the time talking about how you can use this to prepare thermal states of the harmonic oscillator, as this is the most straightforward system to understand. And then if I have time, I'll try to get through some of these generalizations to other systems, and more, actually it works for non-degenerate systems, and maybe some numerics that we also were able to do. Okay, so the classical algorithm that we used for inspiration starts off with the Metropolis-Hastings algorithm, which, if you aren't familiar with it, is just a way to prepare ground states of quantum systems. So you can imagine you have some spins like this, and maybe they kind of represent a magnet, and magnet manufacturer comes to you. They have this new architecture that has, I don't know, maybe 2 doped sites or 2 different spins, and they want you to test numerically. So when does it lose, like, say, 1% of its strength? Okay. So the way you would do that is you come up with some thermal average of your magnetization. You average across all the different spins and the different temperature that you're interested in. And maybe you want to find when this ratio is greater than 99%. Oh, hold up. Does anybody know how to get rid of this bar?
Right, click on it, hide bar or something.
Oh, okay. I think we're good. Okay. Yeah. And so now the difficulty is, well, one, how do you actually evaluate this integral? Because you have to average over all of your spins, which is intractable as the number of spins grows. And you also have to compute these quantities, which computing these is difficult. But the way you get around this is you can essentially just use importance sampling to convert this large integral into a finite sum. And Metropolis-Hastings gives you a way to estimate these different states. Sorry. Metropolis-Hastings gives you a way to estimate these states, SI, with the same probability as the Boltzmann distribution. Okay. And so it breaks down this probability, this Boltzmann distribution, into 2 states. One where you transition from a given input state to another. So for example, you maybe pick a random spin and you rotate it. So it would be like the blue one. And then you filter out. So you take your new state and you compute the ratio of these probabilities, and you accept the state with that ratio, and you clip it at 1, obviously. And the nice thing about Boltzmann distributions is that this ratio scales exponentially with the energy difference. So if you go down in energy, so S2 is lower than HS1, then you will always accept your sample. And so this kind of moves you to higher probability areas of the distribution. And so the way you can show that this converges to the Boltzmann distribution, the Gibbs state, is through this condition known as detailed balance. which it's pretty straightforward to see. You just plug in the thermal state and you do the math and you show that it's fixed. So one of the downsides of this is that this random state transitions is not good because you're only ever locally moving in your state space. And as the number of dimensions grows, this kind of starts failing. And so one of the more newer approaches that avoids this random walk-like behavior is known as Hamiltonian Monte Carlo, which is where you augment your state space. So you take your spins, and maybe now you consider their angular momentum. And what you do is you use this to just evolve the time dynamics to generate a new sample. And so one of the things that this does is you split your Boltzmann distribution over the entire Hamiltonian up into your angular momentum, and then your initial, your potential or your spin-dependent energy. And this is now just a Gaussian random variable. So at each kind of sample step, you can just sample a Gaussian, time evolve, and then get your new sample. And so the nice thing is that when you actually plug into the filtration, Hamiltonian evolution conserves energy. So you pretty much always accept your new sample, up to like numerical errors, obviously, with finite integration. And so this avoids the random walk behavior and has much better scaling with the dimension. And empirically, it just has less correlated samples. So you have a much shorter burn-in period, if you guys are familiar with that. Okay. And so when we tried to port this over to quantum, our first attempt was, well, okay, well, let's take our quantum system rho. Let's add in some random momentum kicks, and then we'll time evolve. And we'll see if that gets us to the thermal state. This is just the Gaussian probability of sampling your random momentum kick. And the problem is that we were able to show after like a year of work that the output is actually further from the target than the input. So that it just clearly does not work. And every state was kind of converging to the maximally mixed state. So we were just throwing away all of this information. And so the solution to this is we need to come up with a better model for the environment. And the way we went about that was what we said, okay, let's take our quantum system, let's look at just a harmonic oscillator, and then let's see what happens if it just randomly interacts with a bunch of other harmonic oscillators. So this is kind of like an ETH style argument that we attempted. And the idea being that if you let these oscillators kind of evolve over time, when you look at like a single oscillator, it should have a thermal state. But this proved to be like way too complicated. Like, how do you actually construct these interactions? Yada, yada, yada. So we said, okay, when does one harmonic oscillator thermalize another harmonic oscillator? And even that was too hard. So we said, okay, well, when can a qubit thermalize a harmonic oscillator? And so now we kind of have two questions. One is, how do we choose the environment? We just have one energy gap. And then how do we choose the interaction? And the interaction that we chose was inspired by this Gaussian unitary ensemble, which is essentially a universal distribution over Hermitian matrices. You can think of it as having Haar-random eigenvectors. So these are eigenvectors that are rotationally invariant about any unitary. And then it has Gaussian IID eigenvalues. So just, just normal Gaussians, nothing crazy. The key idea is that they're not correlated. Okay, so we took that, and then we took a thermal state for the qubit, and then we just time evolved. And if we trace over this qubit and we average over this interaction, this constitutes the channel. And so it's pretty straightforward. It's just, preparing this thermal state of a qubit is very easy. And then doing these time evolutions should be pretty easy. There are techniques for, sampling some of approximations to these distributions. Okay, so now what we need to do is show that it does actually prepare the thermal state. And so the way we went about that was doing a weak coupling expansion. We just took a Taylor series, and turns out we had to truncate it at order 2. The reason being is that the first order terms are 0. One way you can think of that is if you look at the expected value of the interaction, because the eigenvalues are Gaussian, the expected matrix is 0. So you can think of this as sort of 1 order of G. This is sort of 2 orders of G, and this is everything else. Okay. And so now this constant term, this is just if you have no interaction, you're just doing Heisenberg evolution. What we're going to do is we actually want to choose states rho, so input states to the channel that commute with this time evolution. So if it's diagonal in the Hamiltonian basis, then this map or this constant term is just the identity. Okay. So now the actual interesting dynamics occur at the second order. And we can compute this for the system environment, arbitrary system environment input, arbitrary system environment output. And we can find that it actually is just a sinc function, which is just sine of x over x. I'm not going to get into how we actually do that. It's just a little bit gnarly, but suffice it to say that this is the actual output. And this is what the sinc function looks like. So the idea being that this input, this is the change in energy from your input to output of the system. This is the change in energy of the input and output of the environment. You just sum those up, multiply by time, divide by 2. So if this is 0, aka your energy is conserved, any system loss or any energy loss in the system is picked up by the environment, then you're going to be very close to the peak. And as this energy difference gets further away from that, you kind of fall off into these like off resonance transitions. So the idea being is we want to drive system transitions as close to this peak as possible, if that makes sense. Okay. But so now, an unfortunate thing is that this is the output of the system environment total. We have to actually feed in our input state and then trace out over the ancilla qubit, and you end up with these kinds of terms. So these terms just capture the environment not doing anything. This captures the environment being in the ground state and then transitioning up. And this captures the environment starting in the up state and transitioning down. And so we want, this is present for all system transitions. We want to find the ones that are on resonant. So this is an example of an on resonant transition where your system starts at some level, the qubit's in the ground state, qubit gains the energy, system drops in energy. And then a similar thing where your environment is kind of going down in energy. Okay. And then the off resonance transitions, like for example, this term, this delta S is never going to be 0, unless you're looking at the same state transitions, but we have a special formula for that, so we need these two to be different. So this is always going to be kind of off resonant. And then similarly, if your system is like gaining in energy, one of these will always be off resonant. Oh, they're supposed to be, oh, you can barely make them out. These, they're supposed to be little frowny faces or little double emojis representing these off resonant transitions. Okay, so anyways, once we isolate these on resonant transitions, we kind of collect them up into a transition matrix, which is going to be that identity plus T on, and we can just compute what this transition matrix is exactly. And so this is for the harmonic oscillator. And you can kind of see that if this is sort of the ground state input, first excited state input, so on, this is kind of the probability that you, or the transition amplitude for staying in the first excited state. And you can move down in energy or you can move up in energy. But what's nice about this is you can actually compute what the fixed point of this map is. And you can just feed in the thermal state, and in a couple of steps, you can show that the thermal state is actually the fixed point. And then to show it's the unique fixed point, you can show ergodicity of the map, which just means that there's some probability of transitioning from any state to any other. Okay. And so what that tells you is that if you repeat this channel enough times, you're going to converge to the thermal state. So you need to bound how many times you need, how many interactions you need to actually converge, and that will let you bound errors. So in order to bound the number of interactions you need, there's just theorems for this from Markov chain theory. And the one that we use tells us that the number of interactions, L, has to be greater than the dimension over your spectral gap. So whatever the spectral gap of this big matrix is, which we can just compute as alpha squared T squared over your dimension, and then times this temperature dependence. So this lambda star of beta is going to be the spectral gap of just this beta dependent bit. Okay. And then once you have that, it guarantees you that the output of this on resonance mapping is going to be less than epsilon. Oh, I guess I also forgot to explain these. So this is just doing like a triangle inequality and pulling out your L, which is nice because then now we just have to bound each of these two bits separately. And so once we've bounded the Markov bit, we can move to the error terms, which are the off resonance errors and the remainder errors from our weak coupling expansion. And so I'm going to spare you how we computed these, but we can show that the remainder error is of order alpha t cubed times some dimension. And then the off resonance is of order alpha squared over your oscillator gap. And so what we want to do is we want these asymptotically to be comparable, right? So this tells us that if we set alpha to be of order 1 over t cubed, then these will kind of have similar scaling. And then once we set our time to scale like 1 over square root of epsilon, this guarantees us that our total output will be of O tilde epsilon. And this is just hiding logarithmic factors. Okay. And so just by adding these two together, we would see that the total output of the channel will be close to the thermal state. Okay, so this is just a recap of how we went about it. So we just couple it with this gamma. We compute the transitions with this weak coupling. We divide the transitions to on and off resonance, show that the thermal state is a fixed point, and it's ergodic. Use Markov relaxation to bound their interactions. And then this allows us to control the error. And then finally, we could wrap this all up into a nice, neat little theorem that tells you how many interactions at times the time per interaction you need to actually converge to the thermal state. Also, one last tidbit I forgot is that you can show that matrix, that beta dependent matrix, that its spectral gap approaches 1 as the ground state or as beta goes to infinity, which is actually a pretty neat feature. A lot of other thermal state prep routines, kind of bounding that ground state mixing time is very difficult. But for ours is straightforward. It just pops up along the diagonal. Okay. Okay, cool. So I can show you guys some plots. So this is what happens if you look at the temperature dependence of this algorithm at a fixed epsilon, fixed alpha, and fixed t. So over here, this is for a dimension 4 harmonic oscillator, so pretty small. The dashed line is kind of what happens if you throw away all of the errors and you look at just what the Markov chain predicts. The blue line is if you include these errors and simulate the total channel. And we can see it agrees very well. The interesting bit is that beta going to the right is temperature going down. So what this is saying is that you can cool states close to the ground state much faster than you can cool these like intermediate regimes. It kind of doesn't really make much intuitive sense, but we kind of have two factors at play here. One is we always start from the maximally mixed state. So we always start from the beta equals 0 state. And then as we move our target temperature, our input state and our target state are moving further apart. So we have some amount of distance that we need to cool. And while we change this beta, the spectral gap of the Markov chain is apparently also increasing. And as your spectral gap increases, you need less interactions to actually cool. So these two forces kind of counterbalance each other at a certain point. And this behavior becomes more pronounced as you increase the dimension. So this is for a dimension 10 harmonic oscillator. We have no idea if this is actually a generic feature of other quantum systems, but it pops up for the harmonic oscillator. The other thing that we don't know is where this peak is located. The oscillator that we use has a gap of 1, so it's kind of near 1, but no idea. So it's kind of just still an open question. And so lastly, another thing that we checked was how good our error approximation is. So like I said, we use this third order or the second order Taylor series. So, and then what we're able to compute is that if you use a second order Taylor series, your remainder term is of order alpha t cubed, which when balancing these error terms requires you to set alpha to be the certain order of t, which then gives you a certain total simulation time, like that. So that would correspond to this green line, where we set alpha equals 1 over t cubed. And we can find that the slope in the log-log plot kind of matches that factor in the epsilon. It's off by a little bit, but like this is also a pretty big range of epsilon. So what we kind of can conjecture is that the third order moments, because these kind of depend on the moments of the eigenvalues, Gaussians have third moment of 0. So it seems reasonable to believe that this third order remainder will also be 0. And we can kind of repeat a similar process to find a value of alpha that should work and compute the similar value of total simulation time. And we find that that actually matches up almost exactly. And then lastly, our hopes and dreams are that all of this randomness that we're adding actually doesn't hurt you, really. It kind of just shuffles your probability around. So if you believe that the randomness doesn't actually hurt, and that maybe this remainder should be 0, then you could always set alpha to be of order 1/t. And that would give you a square root 1/epsilon to the square root power scaling. And that's actually what we can numerically observe if we do this setting. Okay. Then lastly, these are some theorems showing how you can generalize it to arbitrary systems. One of them is where you assume that you have eigenvalue knowledge. So you can sample an eigenvalue, sample another one, set your environment to be the difference. And we show that you can actually compute the thermal state as an approximate fixed point. You can bound the runtime. And then we can show if you have absolutely 0 knowledge, you can just uniformly sample from some interval containing all of your eigenvalue distributions. That gives you another simulation time. And it's clearly just much worse asymptotically. So you can have a lot of savings by actually knowing what's going on. These are what we plotted actual hydrogen chains, so slightly realistic benchmark systems. Main takeaway is that this orange line is our analytic prediction. This line is our strong coupling expansion. So strong coupling seems to converge much faster with a higher error floor. And so exploring that should be a fruitful area. And this is just exploring the effects of noise on your environment. We can see kind of like a nice interpolation between those two previously shown theorems. And so, yeah, that's kind of about all I had to show. This is the conclusion. Yeah, so the basic idea is take Hamiltonian Monte Carlo, make it a quantum algorithm, show that the underlying Markov chain actually prepares thermal states, and that we can do this for kind of any system at any temperature and use only 1 qubit. So, yeah, that's about all I have.
Questions? Can you tell us a little bit more about the no-knowledge algorithm? So you have an N-level system, you don't know anything about its spectrum.
Mhm.
You have an N-level system, you don't know its spectrum.
Nope.
So what would be the process to normalize it every time you come with a ancilla with random?
Yeah, so the process is you have some upper bound on the spectral norm of the Hamiltonian. So like maybe what the largest or absolute value of the smallest eigenvalue is. You kind of multiply that by 4. You pick a random number in between that range, and you prepare your ancilla qubit in the thermal state with that spectral gap. You time evolve it, and then you just kind of repeat that process over and over. And then this just says like, yeah, that should work to an approximation.
Okay, yeah, please.
How do you prepare the ancilla qubit in the thermal state?
Oh, so yeah, we can just do I think an X rotation, probably X rotation. So it's just, do you mean like an experimental setup or?
Be a mixed state, right?
Yes.
So, like, I don't know how you can do it.
So for a single qubit,
Have to tangle this environment.
yeah,
You prepare a Bell state,
prepare an L state.
and trace over with subsystems.
Yeah, so you could do that to prepare the maximally mixed state.
And in general, you can use that same trick to prepare any purified density matrix.
Yeah, that should work.
Last question.
Can you go back to the classical version of this, which is like Hamiltonian thing? Could you explain a little bit more about how it works?
You mean this one?
Yeah, yeah, yeah.
So what part's confusing?
So you turn your spins into like variables which are like continuous, right?
Yes.
And then
Oh, so you could also think of these as like classical spins.
yeah, like classical. And
Yeah.
then you evolve them according to
We just evolve them according to time. The whole idea being that if these are classical spins, when you do Metropolis Hastings, you're only ever considering where the spin is pointing. You're not taking into account like a momentum, because you're just trying to find the lowest energy configuration, which should be steady state with respect to time. So you just kind of consider its position. This says that if you consider the momentum, this allows you to transition to new states a lot more efficiently.
so you're treating them as classical spins with like some kind of solid object with like momentum.
Yeah.
And you randomly kick them sort of.
We randomly sample the momentum. So it's kind of like you would stop it and then randomly change the momentum to some Gaussian eigenvalue. The idea being that this Gaussian, when you prepare it in the momentum state, the time evolution kind of shuffles this temperature over into the position coordinates.
Okay, thanks.
Yeah.
This was a classical. It wasn't supposed
Yeah.
to be one and two.
Yeah. This is entirely classical.
Thank you very much.
Yep.
Now switch to Shreyas. We'll just give him the, okay, yeah, you can use them. So Shreyas, I know you are supposed to talk fellow in Alchemist Minds.
Yes,
Can you tell us a little more where you came from?
I was working with Nandini Anant and Cornell University. Nandini Anant and Cornell University in semi-classical dynamics.
Shreyas comes from Cornell, where he is. Not a device.
Yes. Thank you. This did not look like I made it.
There's sometimes problems on supporting over.
Oh.
Oh, it's also on the Chrome tab. That works.
Should I download it and then? This is downloaded?
Yeah.
Okay. It looks very different from how it. It's okay. We'll make it work.
Any chance to drag the bar from the center?
Yeah. So the fonts are just going crazy. I don't know what's happening.
Not doing it well. If it's okay for other slides, should that be okay?
I think it's fine. That's
Like-
just like a different aesthetic look, but
Oh, no.
yeah.
Okay, let me try to open it again.
Oh,
That means it's just not translating well to the,
yeah, Shreyas, yeah, we'll try.
Yeah,
That.
we can try.
that's okay.
Yeah.
Is it possible if can I present on my laptop? Is that an
I
option?
could try to. If you can just open your laptop, do you have the Zoom link?
No, I do not have the Zoom link.
Does anyone? The Zoom link is very long. There's a password on it, so I can't just.
I think you can just form it into like a PDF, or you might be able to present it in Google.
In Google Chrome,
Um,
like maybe just open it in the email and
mhm.
yeah, this looks better.
Oh,
Yeah, yeah,
awesome.
yeah, probably.
Yeah, the Zoom link, if you will.
Oh, okay.
If this doesn't work, maybe we'll do the Zoom link thing. But show.
Yeah, this looks
Yeah.
better.
Okay,
Yeah.
now we just have to share it.
I also sent you the Zoom.
Okay, thank you.
Share. Okay.
That's what we have.
Mhm. 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 Do the clicker. There you go.
Okay,
Okay. There you go.
thank you.
Should be. Is it not working?
It's working here.
Okay.
Maybe not on the,
No, it's working.
okay, great.
Okay.
Huh. Thank you so much.
Oh.
Okay, sorry about that technical difficulty. Okay, so today I'm going to tell you a little bit about our efforts to simulate vibrational dynamics, specifically on bosonic quantum devices. And before I jump into this topic, I briefly want to motivate why we need to do this by talking about some experimental quantities that chemists care about, right? So as chemists, we care a lot about reaction rates, and it's not moving now. Okay. Yeah, we generally care a lot about reactions and specifically about the rates of the reactions that we look at. We want to know whether the reactions we are interested in go fast, go slow. And so here I'm showing you a very simple reaction of a hydrogen exchange. And I'm plotting the log of this reaction. The fonts are again messed up, but we'll try to make it work. I'm showing you the log of the rate of this reaction as a function of temperature. And I'm the point that is highlighted here is the rate of the reaction at, let's say, around room temperature. And you see that the classical prediction for this rate is about 2 orders of magnitude off. And so as you can expect, this is because this classical theory cannot predict tunneling that is important in this reaction. And so this is one example where nuclear motion needs to be treated quantum mechanically for an accurate description of the problem. Although my slides look fine here, they are not looking so great here. So please pardon the weird looking slides and the lack of animations. Okay, another example is vibrational spectroscopy. So chemists use vibrational spectra extensively to characterize molecules and maybe even identify different kinds of functional groups in the molecules. So here I'm showing you 2 examples of vibrational spectra for small molecules. And you can see that the classical prediction, which is shown in blue, does not match the quantum prediction, which you can barely see. It's like this gray blob here. And so again, another example where just a classical description of nuclear motion is not enough and you need a quantum description. So with these 2 examples, hopefully I've illustrated that treating vibrational motion quantum mechanically is necessary in many different parts of chemistry. These 2 are just illustrative examples. However, as you will see, we generally solve the Schrodinger equation for the vibrational Hamiltonian to do that. And that will scale very badly with the size of the system. So as you can expect, it scales exponentially with the number of degrees of freedom. And so the approach that we want to take is we want to use quantum devices to solve this vibrational problem that we're interested in. So when we generally talk about the vibrational problem, when we generally talk about quantum devices, we talk about qubit-based devices, right? So that we have a 2-level system, that's your basic unit, and you have access to unitary operations, like qubit unitary operations. And so you can definitely try to put your vibrational problem on a standard qubit-based device. And we actually do that. We are pursuing that actively in a collaboration with Xanadu. But that's not what I'm going to talk about today. I'm instead going to talk about solving this vibrational problem on bosonic quantum devices. So here the basic unit is not a qubit, but instead it's a Q mode or essentially a harmonic oscillator. This hardware also gives you access to different kinds of unitary operations. So instead of qubit-based unitary operations, you now have access to bosonic unitary operations. And just to make this a little more concrete, I want to highlight that these bosonic devices are currently available. So for instance, I'm showing you here a schematic of a microwave cavity that acts as this harmonic oscillator in a bosonic device. And this is basically the bosonic part of the circuit QED hardware. So all this to say that these bosonic devices are currently available. We can use them to solve vibrational problems. And so the natural next question is, so what has been done already? Have people tried to solve vibrational problems in bosonic devices? And again, sorry about the lack of, sorry about the animations being messed up, but you can take one of two approaches. One is an analog simulation, where you have a bosonic device at hand, and you map the Hamiltonian of the device to a system Hamiltonian. The good thing about this approach is that it can easily include anharmonicity. So in general, vibrations in molecules are anharmonic. So that's one good thing about this approach. However, it's limited by the device Hamiltonians you have. In general, your devices can have, you only have access to specific device Hamiltonians. So you can only look at specific systems with these device Hamiltonians. A more universal approach is a digital simulation, where you encode the information about your system in a wave function and in the kinds of unitary operations you do on the wave function. So here on a bosonic quantum device, these unitaries will be bosonic unitaries. And so far, the kinds of simulations that people have presented for the vibrational problem only use specific kinds of unitary operations U that treat the vibrations harmonically. And that's generally a drastic approximation. Molecular vibrations can at times be very anharmonic. They can have couplings between different vibrations, and all that is not taken into account by these harmonic treatments. And so what we are going to, so what we bring to the table is a general framework where you can treat anharmonic dynamics, and specifically for this bosonic quantum computing framework. Okay. So that's basically the setup of the problem. And let's go into a little bit of details now. So we have this vibrational Hamiltonian, where you have a kinetic energy and a potential energy. And to give you a little bit of background for where this Hamiltonian even comes from, you start with the full molecular Hamiltonian. So you have a Hamiltonian including all nuclei, all electrons. You have their kinetic energies. You have their Coulomb interactions. And you perform what is called a Born-Oppenheimer adiabatic approximation. Yes.
Can you say a few words about the instruction set that you're assuming that you have on your bosonic quantum?
Yes, definitely. So let me go to one of my slides here. So as Nathan points out, this bosonic, this is actually yeah, exactly. It's a paper that Nathan is a part of. And so on these bosonic devices, you can basically do universal operations on these bosonic variables. You can you have access to what are called Gaussian unitary operations, which take Gaussian states to Gaussian states, and you also have access to non-Gaussian unitary operations, which take Gaussian states to non-Gaussian states. I'm glossing over a nuance that in this hardware you also have access to both like boson qubit unitary operations. So you can use qubits to perform non-Gaussian operations on your bosonic degrees of freedom. So here's a definition of some of the gates that you have available on this device. The Gaussian ones are relatively easy to perform. The non-Gaussian ones are relatively difficult to perform. So you can think of it as the Gaussian ones are similar to Clifford gates on a qubit device. They're easy to perform. The non-Gaussian ones are like a T gate, non-Clifford gates. They're difficult to perform. Yeah. Can I go into slideshow mode again? Yeah, okay. Back to the Hamiltonian. You start with the full molecular Hamiltonian. You have both electron and nuclei. And then you perform what is called a Born-Oppenheimer approximation. This is based on the fact that nuclei are about 1,000 times heavier than electrons. And so you can imagine that if you're concerned with nuclear motion, then you can think of the electrons as instantaneously adjusting to your very slow nuclear motion. And so with this approximation, you can break down the full molecular Hamiltonian into, like, you can solve for eigenstates in two parts. You first solve the electronic part, and as a result, you get these potential energy surfaces that your nuclear motion will happen on. and then you can solve your nuclear parts or your vibrational parts separately. This approximation doesn't always work. There are situations where you need to go beyond the Born-Oppenheimer approximation, but that's not really relevant to this talk. And so in general, these potential energy surfaces that we get are anharmonic, like I said, and they have couplings between different vibrations. And so that's basically what makes the problem difficult. Yes.
Sorry, what is Q?
So in general, Q could be Cartesian positions of your atoms.
Oh, so
They
like,
could be, yeah, they could be any like a generalized position coordinate. It could be Cartesian positions of your atoms. Generally, we work with what are called normal with normal modes of your vibrations. So you transform your Cartesian coordinates into, in the harmonic approximation, you can assume that your vibrations are uncoupled, and that corresponds to normal modes of vibration, right? Yeah. Okay. So that's the Hamiltonian we are going to work with. We are going to keep, so in the harmonic approximation, you would only keep up to quadratic terms in this potential. We go beyond the harmonic approximation. We start with keeping up to quartic terms. The framework can be extended to higher order terms, but even quartic terms already give you access to interesting potentials. Okay, so with that said, we want we want access to the propagator of this Hamiltonian. That gives you that lets you perform dynamics on a quantum computer, or it can also give you access to the eigenvalues using something like quantum phase estimation. So that's the goal that we are after, getting access to the propagator for this Hamiltonian. And one way to do that is to just diagonalize the Hamiltonian, right? If you can diagonalize the Hamiltonian, then you can exponentiate it as shown here. However, that's the problem we started with. We didn't know how to diagonalize the Hamiltonian. That is why we need a quantum computer. And so this is not a valid strategy, or a feasible strategy, I should say. And so here's the approach that we propose. We say that if we can break down our Hamiltonian into what we call solvable fragments, then we can go ahead and construct the propagator. And we call these fragments solvable because we know how to exponentiate them. So we know how to diagonalize them. And we also know how to implement them on these bosonic devices. So if you can do that, if you can find these solvable fragments, then you can use the Strater approximation to build the Hamiltonian as a product over the propagators for your fragments. And you can, in principle, make the Strater approximation as accurate as required by making the time step for this propagation small enough, right? So with that being said, the only step that's left now is how do we find these solvable fragments? How do we break down the Hamiltonian? And so for that, I want to start with a simple example. So let's say your Hamiltonian is harmonic. You only have two harmonic oscillators that are now bilinearly coupled. This is a simple solvable problem. I'm sure people have seen it in their, like, I don't know, some basic physics course. You take the harmonic oscillators and you rotate them into these normal modes, and now you have uncoupled harmonic oscillators, right? And this unitary operator that I'm calling UB is the normal mode unitary that does this rotation, right? Once you can make it diagonal, you can exponentiate it as I'm showing here. Okay. But this is a simple harmonic example, right? We want to go beyond harmonic oscillators. However, even to go beyond harmonic oscillators, we are still going to use these unitary operations that I mentioned here. So in this case, it's a normal mode unitary transformation. But in general, you can still work with unitary operations that are a little more general than a normal mode transformation. These are called Bogolubov unitary operations. So you can think of this as, in a normal mode transform, you just take all your positions and you mix them with each other. You take all your momenta, you mix them with each other. In a Bogolubov unitary, you take all your positions and momenta, and then you mix all of them together, right, in general. And so it's more general than a normal mode transformation, but it's still easy to perform on a classical device and on a quantum device. On a quantum device, you can break down this Bogolubov transformation unitary into these Gaussian gates that are relatively easy to perform on a bosonic device. So what we want to do now is we want to find solvable quartic fragments. So we are now going beyond the harmonic approximation, And we want to, so I want to highlight here that in general, a quartic Hamiltonian will not be diagonalizable with a Bogolubov transform. However, there will be special quartic Hamiltonians that will be diagonalizable using a Bogolubov transform. And so we construct those special Hamiltonians. And this is the form we use. The term in the brackets here is a quartic term and it's diagonal. And we sandwich it between Bogolubov operators so that it looks like a general quartic term. So even though the Hamiltonian looks complicated, it has all kinds of terms, quartic, cubic, all the way to linear. We have specifically constructed it so we know how to diagonalize it. And so given this form now, all that's left is to break down your Hamiltonian into these fragments of this form. So there are parameters built into this Bogolubov transform. There are parameters built into this fragment, and you can optimize over these parameters to find such fragments. So that's the procedure. Given a Hamiltonian, we find fragments of this form shown here. Once you find these fragments, all that's left is to build your propagator. You build your propagator by stringing together these propagators for each fragment. And then you have an expression of this sort, where these Bogolubov unitaries came from these rotations. Again, like I said, they're straightforward to implement. They just correspond to Gaussian gates on a bosonic device. The unitaries that come from the fragments themselves are quartic, and so they are a little more difficult to implement. But again, in Nathan's paper, they point out how you can break down this so-called cross-care interaction into simpler, easier to implement bosonic gates or even qubit boson gates. Yeah. So the quartic term is a little trickier, but you can still do it. Yes.
Certain types of anamorphic
Mhm.
potentials can be mapped into problems of this type.
So I think we don't have a proof, but I think what we have found, at least in our experiments, is you start finding these fragments, and then the left, like once you write your Hamiltonian as a sum over these fragments, then you can't exactly get your Hamiltonian back. You have some sort of like a small piece of the Hamiltonian that's left over, and so given a tolerance of h original h minus sum over fragments, you can throw away a small piece of the Hamiltonian and still get a sum over fragments. No, they are all both the Hamiltonians and the fragments themselves are quartic, but the coefficients that now show are left are extremely small, and you can make them smaller and smaller by finding more fragments. So the optimization involved is greedy. So you start with the biggest piece that looks like this, and then you are left with a smaller Hamiltonian, and then you keep going to smaller and smaller fragments. Okay, and so basically with this procedure, we have set out to do what we wanted to do. You take the Hamiltonian for your vibrations, and you've mapped it out onto these elementary bosonic unitary gates. So we test this approach out on two simple problems. The first one is tunneling in a two-dimensional well. So this is a model for a proton transfer reaction in this molecule tropolone. The left well corresponds to the hydrogen bonded to the left oxygen. The right well corresponds to the hydrogen bonded to the right oxygen. And there's a big barrier to go between these two wells, and you can tunnel between the wells for the proton transfer reaction to happen. So we take this Hamiltonian and we perform this fragmentation procedure on it. We find 4 fragments, and again, you can build the propagator using these 4 fragments, and then we actually perform tunneling dynamics. So there was an animation here which is refusing to work, but you can start in one side of the well, and you can propagate it under the Hamiltonian, and you can see that the blue blob, which is the density in position space, coherently tunnels to the other side and then tunnels back to the other side. So that's a first toy model that we work with. And then we also looked at fragments for small molecules. So we go up to four vibrational modes here. So the CO2 molecule with 4 modes, that's the biggest system we look at. And now we compare the number of fragments that we find for this bosonic framework with a similar framework for a qubit device. And so even on a qubit device, you can fragment your Hamiltonian and implement the fragments individually. And you see that the numbers of fragments is less than 10 for the molecules that we've looked at. They're in the hundreds, 50s to hundreds for the qubit-based device. And so you have fewer fragments on the in the bosonic case, which is an argument for the algorithm could be cheaper on a bosonic device. Further evidence that this bosonic algorithm could be cheaper is, oh wow, these numbers just aren't there. So unfortunately, these numbers are not there, but the numbers for the non-Gaussian gates, so these are the difficult to perform gates on a bosonic device, are in like 30s and 40s. Take my word for it. I'm sorry. And the numbers for these T gates for a similar approach on a qubit-based device are hundreds of thousands, maybe tens of thousands. So you have 4 to 5 orders of magnitude fewer difficult gates. So the non-Gaussian gates in the bosonic case, T gates in the qubit case. So just switching devices is giving you a very significant speed up here. Obviously, just the cost of one trotter step is not the cost of the full simulation. The number of trotter steps might be very different. The fidelities of the gates are much worse for these bosonic operations right now, if I'm not wrong. And so it's not a direct comparison, but I think it is still a valid comparison. Okay, so with that, I would like to summarize that we have developed a framework to implement the vibrational propagator, importantly for anharmonic potentials on these bosonic devices. The approach we take is we fragment the Hamiltonian into solvable parts, and we construct the propagator using the trotter approximation. And on the test that we perform, we see that it's significantly cheaper compared to compared to qubit-based approaches. And so with that, I'd like to thank my co-authors and collaborators. And thank you, Nathan, for pointing me to a lot of this literature. And thank you all for your attention. And sorry about the slides.